In this video, I want to talk about the Michaelis-Menten mechanism and how that can be used to derive a rate law that explains the way enzymes work. This particular mechanism is attributed to two chemists. A German, Professor Michaelis was a German, Professor Menten was Canadian, and she was a pioneer in biochemistry. The mechanism is rather simple. It applies to every kind of biochemical reaction that we know about. So literally 1,000 different reactions can be explained by this mechanism. And it goes something like this. First of all, in the first step, we have something called an enzyme interacting with the substrate and forming a complex. Now this complex is some small molecule that we want to break down into its component molecules. Perhaps if this were a part of digestion, using that as an example, this could be a molecule that we're trying to derive amino acids from as the building blocks for other substances. The enzyme itself is a really large molecule, many more times the size of the substrate. It has a lot of complexity to it, and there are pockets within the molecule, the enzyme, that the substrate can fit into. And there's a particular pocket where if the substrate goes in, then the enzyme acts as a catalyst in order to break down the substrate into its products. The first step of the mechanism is just the formation of that complex. And you see it's an equilibrium that needs to be considered, because as the substrate docks, it sometimes simply releases and then docks again. Maybe things line up a little bit better, and then products are formed. So there's this back and forth going on in the first step. K1 is the forward rate constant. K minus 1 is the reverse rate constant. In the second step, which is fast by comparison, this substrate breaks off into these little pieces that I have down here shown. So we've got enzyme substrate, the enzyme substrate complex, and the products as part of the mechanism. If we want to take this mechanism, try to prove it, see if it matches up with experimental kinetics, we would have to use our procedures that we have followed before to write a rate law. And in this case, we will focus on the second step of the reaction and think about the overall rate as being the rate that the enzyme substrate complex breaks down. So we can write rate equals K2 times the enzyme substrate complex, and this is the starting point for trying to derive a rate law. Now the complex itself is an intermediate. It gets formed and gets used up during the process. Therefore, we can't use this rate law as it's presently written. It's merely the starting point of our derivation. What we need to do is find an expression for the enzyme substrate complex using the steady state approximation. We evoked this last time. We know that we can look at the rate of formation of this complex, and over time its rate has to be equal to 0. Another way of writing that is to say that the rate at which it's formed has to be equal to the rate at which it's depleted. And we see that relationship written here in this second line. K1 times E times S. Notice we're going back to the first step and writing the formation of the complex would be K1 times E times S, according to the step 1 mechanism. The depletion of the complex would be given by two components, because there is first the reverse reaction of step 1. That's represented here as K minus 1 times the complex. And then also there's the depletion when the products form in the second step. So plus K2 times E dot S. Now the key to understanding the data that's acquired is that we want to think of the enzyme that's present as at any point in time during the reaction being given by the total enzyme that we initially place in the reaction minus the amount that's tied up in the complex. So when we're doing this experimentally, we won't know E per se, but we'll know how much total enzyme we've added. And therefore we can use this expression to substitute for E in the steady state approximation. We've got to put this quantity here in for E and then solve for the E dot S complex and plug it in to the rate law. Rate equals K2 times that. So it's a algebraic maneuver here that I'd like you to try to do on your own. I'll show you the results of that. We're going to first plug E into the steady state so that we don't have E in our equation. And then we're going to solve for E dot S and plug it into the rate law. And from there, that will generate the famous Michaelis-Menten equation. Pause the video, try to do that algebraically, and come back to check your work. Okay, so here we have the algebra worked out, and see if you can match up your work with what you see here on the screen. We have, first of all, just plugging in that expression for E. We'll have E tote times S and E dot S times K1. That's that first side of the equation. And then the E dot S is multiplied by this summation of the two complex rate constants here. And then solving for the E dot S, we would have here it is by itself, and so we'll take this and solve for E dot S, and that will be equal to what you see here on the left hand side divided by what you see here in parentheses. And so that divided by that is what we plug into the rate law. And so here you see the pieces, right? K1, there's your this is directly this piece right here. And then what we'll be dividing by is that piece there. Once we have this, we can simplify it by dividing through the top and the bottom both by K1. And so we'll be left here with K2 times E tote times S divided by, and this will just become S, and then this in parentheses will be the collection of constants. And this isn't really how you would see the Michaelis-Menten rate law normally. But if we make the following substitutions here, we can see that the K2 times E tote is sometimes together called Vmax, because that quantity, the rate constant for the second step times the total amount of enzyme, that quantity turns out to be the maximum rate at which the reaction can occur. More on that in a second. And this collection of constants, which independently represent the rate constants for the three different steps in the mechanism, When taken together like this, we call that the Michaelis-Menten constant, usually symbolized by a capital K. Now, if we look at the equation itself, this is an interesting rate law. It's certainly not an elementary type of rate law with just reactants raised to particular powers, right? We've got a denominator here. We've got substrate appearing twice. But let me show you how this equation lines up with the experimental data. So we can analyze this equation and compare it to the experimental data. What's normally done is, in the experiment, we will vary the amount of substrate present and measure the rate of the reaction. And so looking at the equation itself, let's think of what this graph might look like. If we begin with a small substrate concentration, then we'll see that there is a linear dependence initially on the rate, that as you increase the substrate concentration, the rate will go up linearly. The reason for that is that at the starting point, when S is very small, in the denominator here, it can be ignored, and Km, the value of the Michaelis-Menten constant, dominates. And the rate would then be equal to just the Vmax over Km times S. That's just linear with respect to S. And the slope of this line would be Vmax over Km. So that's the slope initially, just for the beginning of the reaction. So right there. Now, jump to the other end of the x-axis now. For large substrate concentrations, we'll see that eventually it doesn't matter how much additional substrate you add, the rate no longer increases. That is to say, the data looks pretty much horizontal at large S values. And why is that? Well, again, come back to the rate law that we derived. If S is large, its value is large compared to Km, and the Km can be ignored. And if Km can be ignored, then the S will cancel in the numerator with the one in the denominator, and we'll simply have Vmax as the rate. So this value that this asymptotically approaches will be Vmax. And Vmax, remember, is K2 times E total. So that's Vmax is here. And it's the rate that it asymptotically approaches as S increases. In between, the data is sort of a curved line, and so I'll finish off the graph by showing you what would be collected for this. Now look at what we can get from the experiment, right? First off, by just adding substrate until this, levels off, the rate at which it levels off is Vmax, and Vmax can give us K2 because we know how much enzyme we put in. Vmax is K2 times the total amount of enzyme. So that gives us K2, this value. Once we know K2, once we know Vmax, then the slope of the line initially can be used to get Km. So two parts of the data set are needed. in order to fully flesh out the rate law and get the constants needed to describe the enzyme kinetics. It's very important then that you cover the full range of values for substrate when you're doing this experiment. If you don't go far enough, of course, you're only getting data that gives you the initial slope, and that's not enough to get Vmax, and it's not enough to get K2. So you have to make sure that you've put in enough substrate to get to that limiting case. On the other hand, you can't start out with too much substrate, because if you were to begin the experiment, let's say in this region right here, you'll not get the initial slope, and so you'll not be able to get Km. So it's very important when studying enzyme kinetics to get a full range of substrate values in order to produce the data that's needed to verify this rate law and get the constants for it. But this has been done now. Thousands of reactions have been studied this way, the way enzymes work, and they all fit to this particular equation, which is why it's one of the top 10 biochemical equations discussed, maybe even top 1 or 2 in importance. This is Michaelis-Menten explanation. I hope it helped. I hope it helps you solve the homework and the quiz question that involves Michaelis-Menten. Talk to you later.